Hello, welcome to another module of this course, Analog Circuits. So, in the past module we had been talking about limiter circuits. In this module I will introduce you to another limiter circuit. So, the other circuit that I was mentioning, suppose we have a op amp in a inverting configuration like this. Now, assume that both D1 and diodes D1 and D2 are open, then the output voltage will be given by minus Rf upon R1 times Vi. Now, suppose for some reason, now note here that this voltage will be at 0 volt, okay, because the non inverting terminal of the op amp is in a virtual short. Now, suppose for some reason the voltage Vo goes on high, okay, it becomes higher, and say Vo is greater than Vd, where Vd is the threshold voltage of the diodes. So, if Vo is greater than Vd, then diode D1 will start conducting, and if diode D1 starts conducting, then there will be a short between these two terminals. If there is a short between these two terminals, then Vo will be 0. If Vo becomes 0, then immediately what will happen? The threshold voltage across diode will become lesser than Vd, and therefore, this point and this point will again, the diode will be in an open configuration, that is, it will not conduct. There will not be the short that existed between these two terminals before will not exist once this Vo becomes 0. Okay. So, the sequence of action is like this: Vo for some reason goes above Vd, diode D1 starts conducting. As diode D1 starts conducting, Vo becomes 0, and once Vo becomes 0, diode D1 again becomes open, and so the voltage, the relationship between Vo and Vi is restored to this form. Similarly, if Vo is lesser than Vd for some reason, then also a similar sequence of events will happen. First, diode D2 will start conducting. Once diode D2 starts conducting, Vo will again be equal to 0. Okay. So, for both these, whenever these two conditions happen, Vo will immediately become equal to 0. Once Vo becomes equal to 0, this diode will again go into the open, that is the cutoff stage, where and these two terminals will be, the short that existed between these two terminals will no longer exist. So, what you see is that I should say this is minus Vd, this is plus Vd, this is minus Vd, just note this correction. So, what we see is that when this V0 is lesser than minus Vd and greater than plus Vd, only then this relationship is true. For other values, this relationship, or in other words, when Vi increases or decreases to such an extent that Vo exceeds this limit, then we can no longer guarantee that Vo will continue to follow this relationship when such a condition happens, that is Vi becomes so high or so low that Vo exceeds or decreases beyond this limit, then Vo will automatically go to 0. Okay. So, then this is the range where Vo can exist, hence this is a limiter circuit also. Okay. So, that was about limiter. We shall see some uses of limiter when we discuss about oscillators. Right now, let us discuss in a little detail about the diodes. Diodes are an example of what we call active circuits, because they need a certain external input power for their operation. Unlike resistance, so just like an op amp which needs a external supply voltage, in diode a certain bias voltage is necessary for its operation. So, resistance, inductors, capacitors, they are all examples of passive components, because they do not require any external power supply for their operation, whereas diodes and op amps do. So, let us study a little bit in detail about diodes. So, diodes, as you know, I have already given you the symbol while discussing the limiter circuits, and diodes are also a prime example of nonlinear components. The input output relationship between inductors, capacitors and resistance is linear, either directly proportional or their derivatives are proportional to the input and output. But in diode, as you have seen already, that it is a non-reciprocal, that is, if just because current flows from one terminal to the other does not mean current can flow from the other terminal to the previous one. So, it is a non-reciprocal network. It is also a non-linear network, because in a diode for some input voltages it conducts, for some input voltages it does not conduct. So, it does not follow the linear relationship, or it does not follow the linearity principle. So, diode is, so then we can write that diodes are an example of non-reciprocal and non-linear component. Okay. Now, ideally, how should a diode operate? Ideally, if you write the input output relationship, then the ideal input output relationship between input voltage and output voltage should be somewhat like this. Okay. That is, whenever Vi is above 0 volt, it conducts, and if Vi is lesser than 0 volts, it does not conduct, or I should say when Vi is above 0 volts, there is a certain output voltage. When Vi is lesser than 0 volts, there is no output voltage, the output voltage is 0. But this kind of characteristic is quite difficult to achieve actually, because first of all, see that how do we determine this output voltage where I said it should saturate, that is somewhat difficult. So, more practical circuit or more practical achievable characteristics of a diode is somewhat like this. If I draw a graph between the current and the voltage of the diode, then at a certain voltage which I call the threshold voltage, it starts conducting, that is, there is a finite current, and below this threshold voltage there is no current. Now, even this is somewhat difficult to achieve actually. Okay. What we do get in reality is something like this. The diode that we actually get in the market has a characteristic somewhat like this. I shall write this term Vd. This is not the same as the Vd, the threshold voltage that we had been discussing. This, I will just give you some of the nomenclature that I am using in this course. I will just mention. If I write a term like this, and like this, what is the difference between these three quantities? When I write I with a small d, this refers to just the AC component or the non-DC component or the time varying component of the current. With the capital I with a capital D, this represents the DC component or the non-time varying component. And small I with a capital D, this represents the AC plus DC. Okay. So, here when I am drawing the characteristics of the diode, I am representing the y axis with small I capital D and the x axis with small v capital D, both representing the AC plus DC component. Now, the equation governing the voltage and the current of a diode at any particular point on this graph is given by what is known as the Shockley diode equation. Now, here this is the DC component and this is also the DC component of the voltage. What this equation gives is that suppose the voltage across the terminals of a diode is kept at Vd, okay, then what will be the Id that is flowing through it. So, this is the steady state or DC characteristics. Of course, we are here assuming that when the voltage across the diode falls below 0 voltage, then current will be 0, though that is not entirely true, but for this particular case, for now we will be assuming that the current is 0. This AC plus DC component of the voltage across the diode can be given as the sum of the DC component and the AC component. This equation can also be simplified like this. Now, here this capital I capital S is a constant. So, this for even moderate values of Vd can be given like this. This equation, if I now represents in place of capital I capital D, that is instead of the DC current I represent the AC plus DC component, then this will approximately be given as Is E raised to the AC plus DC component of the voltage across the diode like this. Okay. Here we are ignoring this one because even for small values of Vd, this exponential term will be much larger than 1. So, then I can write my IDT like this now. Okay. So, here I have simply in place of the AC plus DC component, I have substituted with the DC plus the AC component. So, I can write a small t showing that this small v small d is a function of time. So, this becomes Now, this if I consider this whole thing as a constant, I am assuming here that the DC voltage across the diode, that is we are operating at a particular point in the graph, okay, where the DC voltage is capital V capital D and the DC current is capital I capital D. So, at this point, if we are seeing the applying a signal around this particular DC bias point, as I said, this I will call the DC bias point. Why DC bias point? Because the changes that we shall be observing are about this point. Okay. So, around this point, what is the, if we apply a small AC signal about the DC voltage or a small AC voltage about the DC voltage capital V capital D, then what will be the small AC current we will be observing about the current capital I capital D. So, let us assume that this is a constant, this capital I capital S e raised to V d upon n V t, and let me call this as I d, okay, I capital D, this representing the DC component of the current. Okay. Now, if this exponential term is quite less, then we can simply use the exponential expansion and consider only the first term of the exponential expansion. Okay. So, this becomes equal to and this can be further expanded as. So, we have small I capital D t is equal to I d plus I d upon n V t into V d of t, and this is, now I am representing this whole quantity by I d t. Okay. So, this is the DC component of the output current of the diode current, and this is the AC component which I am representing by small I small d t. Okay. So, what I have effectively done here is that, now see, fundamentally the diode characteristics is non-linear, isn't it? The I d versus V d, as you can see, it is a curve. But about this point I am linearized it. Linearized it means I have just assumed or developed a relationship which shows that for small variations of the AC voltage about the DC bias point capital V capital D, then the output current that we will get for small AC variations, the small AC diode current that we will get is also is linearly related to the AC voltage variation, and that is given by this relationship. So, I d small d t is given by this relationship, which shows that the AC current across through the diode is linearly related to the AC voltage across the diode. Okay. Now, so we had the expression for I d I capital D like this. Okay. If we differentiate this equation, let us see what happens. So, I am differentiating the AC plus DC current with respect to the AC voltage, and what I get is the DC bias point. So, this and say this I call as 1 upon R d. So, this is the AC resistance. The AC resistance is the instantaneous or the dynamic resistance offered by the diode to any variation in voltage. Okay. So, the small change in the current about the bias point due to a small change in the voltage about the bias point is what is measured, is what is given, or the factor that controls this change of current with respect to small changes in voltage is given by this R d. So, this is known as the AC resistance, and it is given by the inverse of this quantity. So, then again if we go back to the characteristics for a moment, what we did was we linearized this point. Okay. So, we drew a straight line about this point, okay, and the straight line also kind of this blue line kind of closely follows the curve also. And if we extend this line so that it touches the x axis, and suppose we the point where this line, this blue line touches the x axis is V d 0, then what will be the equation of this line? So, the equation of this line will be V d minus V d 0 upon R d, since R d is the slope, will be equal to I d minus 0. So, from here we get V d, that is the AC plus DC voltage, is equal to I d R d plus V d 0, from which we get V d 0 plus I d plus I d R d, and from which we get this represents the DC component and this represents the AC component. Okay. Now, if we also write our V d, this V AC plus DC voltage as V d d plus V s, or simply I can write V d plus V s, okay, where V s is the AC input, okay, or I will just follow the convention, I will just write it like this, is equal to V d plus small v d, small v small d. So, this is capital V capital D plus small v small d. Then this V d is equal to I d into R d. Now, let us consider a circuit with the diode in it. Suppose we have a source, an AC source V s and a DC source V d d, okay. With a diode like this, whose AC plus DC voltage is given like this. Now, here if we write the Kirchhoff's voltage equation, what we get is V d d plus V s is equal to, suppose the current is I d. So, this is the AC plus DC component of current. So, this is I d into R plus V d plus I d into R d, from which we can write it as, now this small I capital D is the sum of the DC component plus the AC component plus VD plus ID RD, which in turn is equal to capital I capital D plus R into capital I capital D plus VD plus ID into R plus ID. Okay. See here, this part that we obtained is dependent only on DC currents and voltages. This part, the voltage side, left hand side, is also dependent on DC components, but this component and this component is dependent on the AC currents and voltages. So the circuit which we were given here initially can now be divided into two components. One is like this, and another circuit like this. This circuit is called the AC circuit. This circuit is known as the DC circuit. Note that both these two circuits operate only in the positive bias mode, that is when the diode is conducting. For when the diode is not conducting, of course these two circuits will not be valid. Now coming back to this circuit, see this is the DC circuit. What it means is, if we want to find out the DC operating conditions of this diode, then if we find a solution of this circuit, we will know exactly what is the voltage across the diode. The diode node consists of this entire, all these things. Here on the AC circuit, however, the diode is limited to this part. So this is entire thing is our diode. This is an ideal diode, means whose threshold voltage is 0, and since in our diode the threshold voltage is not 0, it is replaced by this VD0. Now, when finding out the DC operating point of any diode, which is a frequent exercise that engineers have to do, you are given a circuit, what is the DC input and output voltages of a diode. So there, this circuit is useful, as we have seen, and note that this VD0 that we are using is not a point on the IV characteristics of the diode, it is simply a point on the x axis, where the straight line that we used for linearizing the diode meets the x axis. So this is very important, this threshold voltage that we use while obtaining the DC solution of any circuit, VD0, is not a point, note this very carefully, is not a point on the IV characteristics of this curve, isn't it? VD0 is a point on the x axis, you see, it is nowhere on the characteristics. It is just the point where the line or the linearization line used for linearizing this diode circuit about its bias point meets the x axis. So note this carefully. The AC circuit, on the other hand, is quite simple, it just consists of an RD, small r, small d. There are no diodes or threshold voltages. Of course, keep in mind that this circuit will be applicable only when the diode is conducting, that is in the forward bias, what we also known as. So when the diode is not conducting, this circuit will not be valid. Okay. So I hope I was able to explain in a little detail about the operation of a diode. when we try to find out, the important point about a diode is that there is a threshold voltage when we try to, which we have to consider while trying to find out the DC solution of a diode, and this threshold voltage, it derives from the linearization that we do on the diode, not from any point on the IV characteristics of the diode. So, thank you very much for attending this module. See you in the next module. Thank you.